In this video, I'm going to be working BC Homework 12.3, and I'm going to be, working some Taylor series free response that have Lagrange error bound or some kind of error bound component to them. But we're going to start off with write the first degree Taylor polynomial for h around x equals 2 and use it to approximate h of 1.9. Oh, first degree, that's really nice. Okay, so that would be t1 of x would equal h of 2 plus h prime of 2 times x minus 2, and that's the first degree. You divide by 1 factorial, we're done. Okay, so we just got to find those values, and that would be, okay, h of 2 is 80, plus h prime of 2 is 128 times x minus 2. And if we wanted to approximate h of 1.9, we would plug 1.9 into the Taylor polynomial for h, 1.9, which is equal to 80 plus 128 times 1.9 minus 2, and this is free response, we're good to stop there. Okay, write the third degree Taylor polynomial for x around h equals 2 and use it to approximate h of 1.9. Okay, so third degree Taylor polynomial will be the same 80 plus 128 times x minus 2. Then I'll get the second derivative, 488 over 3, divided by 2 factorial, which is 2, times x minus 2 squared, and I'm going to need the next one, which is 448 over 3. Wait, well, yeah, I think I'd probably prefer to just write it like this, times x minus 2 to the third, and there we've got our polynomial. So if I want to approximate h of 1.9, I'm just going to need to carry a bunch of stuff around. Is approximately equal to the third degree Taylor polynomial with 1.9 plugged in, which is going to be 80 plus 128 times negative 0.1 plus 488 over 3 divided by 2 factorial and negative 0.1 squared, and then 448 over 3 divided by 3 factorial times negative 0.1 to the third. Right, now we're going to use the Lagrange error bound to show that the third degree Taylor polynomial for h around x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative 4. Okay, so remember how this always starts. With Lagrange error bound, we always start by saying error is less than or equal to. That's very important that we start like that. Then we're just kind of trying to maximize the next term. Okay, we use the third degree Taylor polynomial, so the next term would have a 4 factorial and something to the 4th power. Now we're going to use absolute values just to make sure that we're not ever trying to say the error is less than or equal to a negative number. Okay, the approximation point that plugged in was 1.9. I was centered at 2. And I usually like to write this off to the side. So we used a third degree polynomial centered at x equals 2, and we approximated at x equals 1.9. So I like to say, next factorial, next power of x0 minus c. So 1.9 minus 2 to the 4th power. And then we need to find up here in the numerator what this would be, but I don't recommend that you write it in, is the maximum possible absolute value of the next derivative on the interval between the approximation point and the centering point, which in this case is 1.9 to 2. Okay, but I don't really recommend you write that, because if you write it, you got to be right. And we're just going to go back to the table and see, okay, on the interval 1.9 to 2, okay, what's the maximum possible value of h's 4th derivative? Okay, and the 4 derivatives are strictly increasing, so that means that it's increasing from 18 to 584 over 9, which I guess is bigger than 18. Yeah, that does make sense. And so the maximum possible absolute value must be that 584 over 9. So I'm going to use that 584 over 9. I guess in this case it was actually h's 4th derivative, but 584 divided by 9 right there. Okay, we don't need that. Okay, we've shown we've got the error, the bound, and then we're going to say that this is less than 3 times 10 to the negative 4. And if we're short on time, we're just going to go with that, and we're either going to be right or wrong based on our error bound, not on the last thing. But if we had extra time and we wanted to figure out, wait, why is this true? Okay, we'll just set up a big fraction. 584 divided by 9 and 4 factorial. And then negative 0.1 to the 4 is going to be 10 to the 4 in the denominator. Okay, so that's where the 10 to the negative 4 is coming from. Let's think about this. 584 divisible, it's divisible by 2 at least, so maybe I'd say, all right, that would be 292. 584, yeah, divided by, and I'll just lose the 2. So 9 times 4 times 3. I guess I could divide by 2 again and say, all right, well, I'm not going to make a new line for this. That would become a 2. And half of 192 would have to be like almost 150. 146. Yeah, 146. Yeah, that feels right. 146 here. Okay, what am I supposed to be seeing here? It's less than 3. 9 times 2 is 18, times 3 is 54. Okay, yeah, and 146 over 54 is going to be less than 3 because we would need something bigger than 150 for that to equal 3. Okay, yeah, the logic's always in there, but it's just a waste of time. And that's kind of my message to you this year, is that just go for the error bound, get it right, say it's less than whatever you're supposed to say, and move on with your life. Okay, because that was a whole arithmetic endeavor that didn't even really pay off all that well. Okay. Now, we've got another one. F has derivatives of all orders for x between negative 1 and 1. Derivatives of f satisfy the conditions below. Maclaurin series converges to f for x between negative 1 and 1. All right, first 4 non-zero terms in the general term of the Maclaurin series for f. Well, what we're going to need to do is just get f double prime of 0. That's going to be where, right here, n equals 1. So negative 1 times the first derivative. So that would be negative 1. F triple prime at 0 is going to equal, that's where n equals 2 back over there. So negative 2 times the previous derivative, so that would be positive 2. And then f's fourth derivative, which is what I'm going to need if I want the fourth degree Maclaurin polynomial, or the first 4 non-zero terms, prime, second, yeah, I need all 4. At 0 is going to be where n equals 3, so negative 3 times the previous derivative would be negative 6. Okay, so the first 4 non-zero terms, so I'd have a 0, but then plus 1x. Okay, f double prime is negative 1, so minus 1 over 2 factorial x squared. Okay, f triple prime was 2. We would divide by 3 factorial x to the 3, plus f's fourth derivative divided by 4 factorial x to the 4. The general term, well, the n plus first derivative, which I guess that's a little tricky, but okay, the n plus first derivative, wait, and the general term of the Maclaurin series for f, wait a minute. Oh, that is very tricky. This is going to require us to do a little bit of simplification. I was like, I don't really see the pattern. It's kind of recursive, so that wouldn't fit very well in an explicit formula for the general term. What we're going to need to do is actually simplify this. 2 over 3 factorial is 2 over 6 is 1 over 3. I forgot that x squared, but then I'll have an x to the 3. 6 over 4 factorial, that's 1 over 4 because 4 factorial is 24. And now I can see the pattern plus dot dot dot. Okay, so it's alternating, so I've got a negative 1 to the nth power. I'm going to have an x to the n plus 1, because I'm assuming I started at 0, kind of, now ignoring that. And divided by, well, the denominator is just the same number as the exponents, so that would be n plus 1. Now, if you wanted to call that negative 1 to the n plus 1 x to the n divided by n, that would actually also work as well, but just don't even worry about that. Determine whether the Maclaurin series we described in part A converges absolutely, converges conditionally, or diverges at x equals 1. Okay, and let me just make sure yeah, the formula I wrote definitely works if you think about it in starting at 0. Okay, and yeah, then so I'm just going to leave that as it is. So I've got, if x is equal to 1, I've got the sum as n runs from 0 up to infinity of, what was it, negative 1 to the n, 1 to the n plus 1. Okay, well, that's over n plus 1. That's just going to equal 1 minus a half plus a third minus a fourth and so on. And that's the alternating harmonic series, which converges conditionally. If this was my AP exam that was determining whether I got 2 credits or not, I would probably give a little bit more reason. I would say, the sum from 0 to infinity of 1 over n plus 1 diverges because it's harmonic, and this one converges by the alternating series test, maybe. But we know that harmonic and alternating harmonic don't require justification in AP calculus, so maybe I would just, say that. Write the first 4 non-zero terms and the general term of the Maclaurin series for g of x equals the integral from 0 to x of f of t dt. Well, what I'm going to do, I'm just going to grab this business right here, especially since I had an extra copy of it, and that was f. And, because g is an antiderivative for f with g of 0 equals 0, because think about plugging in a 0 there, that's going to give me 0. I'm just going to anti-differentiate piece by piece, and there's going to be a 0 in front, because that's the value of c. 1/2 x squared minus 1 over 6 x cubed plus 1 over 12 x to the 4 minus 1 over 20 x to the 5. And these are not factorial numbers, right? They're kind of related, but they're not. So what I would say, okay, first 4 non-zero terms, there we go, and the general term. Okay, we're just going to anti-differentiate the general term of f by adding 1 to the power, negative 1 to the n, not adding 1 to the power of negative 1, because we're anti-differentiating with respect to x to the n plus 2. We were already dividing by n plus 1. We need to add in a power of n plus 2, because add 1 to the power divided by the new power, and there we go. First 4 non-zero terms and the general term. Okay, now Pn is the nth degree Taylor polynomial for g around x equals 0, evaluated at x equals half, where g is what we were talking about just before. Use the alternating series error bound to show, oh, that's a disappointment. Okay, I was hoping it was Lagrange error bound. Okay, but this is an alternating series. Okay, what I first need to do in order to use the alternating series error bound is justify that the Maclaurin series converges. So the sum from 0 to infinity of negative 1 to the n x to the n plus 2 over n plus 1, n plus 2, well, actually with 1/2 plugged in, is the type of series that alternates, because the negative 1 to the n. Okay, the magnitude of the terms decreases towards 0. Okay, and therefore that means this thing converges by the alternating series test, and we can go ahead and use the error bound. Okay, so if I used the 4th degree Taylor polynomial, that would be I used up to n equals 2. So error is no more than the, right, because the 4th degree Taylor polynomial would be, up to the 4th power of x, where x is a half, so that would be n equals 2. So error is less than or equal to the absolute value of the n equals 3 term, negative 1 to the 3, 1/2 to the 3 divided by 3 plus 1 times 3 plus 2. And they wanted us to show that this was less than something, we'll say less than 1 over 500. I will go in and attempt to do the arithmetic real quick. Okay, that negative 1 to the third, 1/2 to the third, so it's going to be 3 powers of 1 in the denominator, or 3 powers of 2 in the denominator. Okay, 5 times 2 is 10, times 8. What? Oh, n equals 3. 3 plus 2 up here. That's going to be 5. I was like, that's not actually less than 1 over 500. Okay, 2, 4, 8, 16, 32 times 4 is bigger than 120 times 5 is bigger than 500 in the denominator, and so that's what they were going for. Okay, I see it now. And so there you go. That if you do check it, that can help you catch yourself in an error, right? Because, oh, wait, that wasn't less than 1 over 500. Okay, and I guess that had I not done that, had I just done what I recommended y'all do, just slap on a 1 over 500, I'd just been wrong. And, but also part of my message is that the error bounds, alternating series, or Lagrange are really not going to be like making the difference for us between, getting credit and not getting credit, or getting a 5 and not getting a 5. I really don't think that's the case for anybody, at least in my class. Okay, so let f be a function having derivatives of all orders for all real numbers. Third degree Taylor polynomial for f around x equals 2 is given by this thing. Find f of 2 and f double prime of 2. So f of 2 is going to equal 7. This is what we did a lot in the last lesson. And then for f double prime, I want the thing that's connected to the, actually maybe I would do that. Thing is connected to the x minus 2 squared term. So f double prime of 2 divided by 2 factorial multiplied by x minus 2 squared is equaling -9 times x minus 2 squared. First order of business, get rid of the x's, then multiply both sides by 2 factorial. So f double prime of 2 is going to equal -9 times 2 factorial, which if you wanted to multiply that would be -18, but you wouldn't have to. Is there enough information to determine whether f has a critical point at x equals 2? Yes, there is, because I can say that I know f double prime of 2 equals 0 because of the missing x minus 2, f prime, pardon me. Know that f prime of 2 equals 0 because of the missing x minus 2 to the first power term in the Taylor polynomial. Okay. Yes, so yes, there is a critical point because f prime of 2 equals 0. If so, determine whether f is a relative maximum, a relative minimum, or neither, and justify my answer. Well, I've got f prime of 2 equals 0. I just showed that f double prime of 2 is less than 0 above. Therefore, I've got a relative maximum. Okay, because I've shown that the graph is flat while being concave down, which must be a maximum. Okay, now use t of x to find an approximation for f of 0. Okay, well, that should be pretty easy. I'm going to say f of 0 will be approximately, that's really bad, equal to t of 0, which would equal 7 minus 9 times -2 squared minus 3 times -2 to the 3. Okay, and that's my approximation. Is there enough information to determine whether f has a critical point at x equals 0? Absolutely not. Okay, the Taylor polynomial is only giving us information, if it's centered at x equals 2, it's only giving us information about the derivatives at x equals 2. I don't love this question. I've seen another version of this question somewhere in AP Classroom. I don't love this question because I know that y'all recognize that there are like higher levels of math out there and you don't know exactly what you don't know at this point. But I'm telling you, you do not have enough information to determine anything for sure about f besides at the centering point based on the Taylor polynomial. But if not, explain why not. No t of x gives data about f's nth derivative at 2 for n between 0 and 3. Okay, that would be my reason. Then now I've got a Lagrange error bound question to explain why f of 0 is negative. Okay, now this must have allowed a calculator or something. Yeah, a calculator allowed. I'm not going to use a calculator because it'd be faster for me to just do this by hand. But I'm going to say f of 0. I'm going to do that approximation real quick. 7 minus 9 times 4 minus 3 times -8. So that would be plus 24. So 7 minus 36 plus 24 is 7 minus 12 equals -5. Okay, so that's what you really needed to do with the calculator on this problem. Okay, Lagrange error bound from approximation from part C. Yes. Okay, and we have that maximum derivative that we need. We're going to plug in that 6 in the numerator. So we're going to start off with error is less than or equal to, because we always do that. Okay, there's going to be a fraction. We used a third degree polynomial, so the next term would have been the fourth power. So I'll put a fourth factorial, absolute value of something to the fourth. We plugged in x equals 0, and the Taylor polynomial was centered at x equals 2. So n equals 3. So use the third degree Taylor polynomial centered at x equals 2 to approximate at x equals 0. I have to always put that information off to the side. And there we go. All right. And then the numerator is just going to be, that 6 here. And this is the only one of these that I'm familiar with to explain why f of 0 is negative. So we've got the Lagrange error bound right here. I might just go ahead and simplify this because 6 over 4 factorial is going to be 1 over 4. 2 to the 4 is 16. So I've got error, and this is a good idea of something else that a person could do with Lagrange error bound besides just what you usually do in AP calculus. Error is less than or equal to 4, but my approximation was negative 5. Okay, and so basically the true value is somewhere in between negative 9 and negative 1. That's range of possible values. Of f of 0, which is still negative. So really when we're saying error is less than or equal to 4, I would say f of 0 is going to be between my approximation minus the maximum possible error and my approximation plus the maximum error, which is still less than 0. Okay, there you go. That would be like the most formal way to show that. And there you go. Okay, so let's keep it going. I think this one's got a Lagrange error bound. No, an alternating series error bound. Okay, this one's a pretty long one. Let me see. How many of these do we have? Let's see. We've got 6 total, and I just did 3. I'm going to call it for this video, get myself something to eat, and come back with another one in a new video. So thanks for watching.